Hi class, it's Mrs. Kane. In this video, I'm going to be introducing you to the next unit, which is Unit 5, and we're going to be talking about rational functions. So if you want to take a moment to create a new folder in Notability, as you send this document from Schoology over to Notability, you can call it Unit 5, Rational Functions. And in this first lesson, we're going to talk specifically about the graphs of rational functions, and we're going to use the graphs to establish some new vocabulary. All right, so first of all, what is a rational function? So a rational function is of the form y equals n of x over d of x. Okay, and n of x and d of x are polynomials. So they could be constants, but they could also have variables. And because you could have variables, we have to make sure that d of x does not equal 0. So notice n and d, numerator and denominator. So you have to make sure that when you have a rational function, the denominator does not equal 0. Okay, so to introduce some of the vocabulary, we're going to look at 3 different rational functions. I'm going to have a picture of the graph given. We're going to go over some of the vocabulary, and we'll talk about how we can find each part from the equation. So the first function is f of x equals x minus 1 over x minus 2. So first thing I'm going to do is add arrows to the ends of these graphs here. I made this graph on Desmos, but I had to cut it off and I couldn't get the arrows on there. So the graphs, these branches are supposed to keep going in those directions. Okay, so the first thing it tells us is that the function f of x has a vertical asymptote at x equals 2. So let's take a look at what happens when x equals 2. All right, so when x equals 2, we have a vertical asymptote. So I want you to sketch a dashed line, vertical line at x equals 2. And what I want you to notice is that the branches approach this line but never touch this line. And the reason is that 2 is the value that causes the denominator to equal 0. Okay, so the function has a vertical asymptote at x equals 2 because that value needs to be restricted. So when we look at the graph, the vertical asymptote is a line that the graph approaches but does not touch. Okay, so this is where d of x equals 0. Okay. All right, so next it says that the function has a horizontal asymptote at y equals 1. So let's go ahead and draw in y equals 1. So that would be a horizontal line through y equals 1. So draw another dashed line. And notice again, the branches approach but do not touch this line. Okay, what the horizontal asymptote tells us is what happens at the ends of the graph. So if you look at the left side of this graph, let's go back to our end behavior. As x approaches negative infinity, the function approaches 1. Okay, the branch is flatlining at y equals 1. And you'll notice that the same thing happens on the right side of the graph. As x approaches positive infinity, the function is also approaching 1. So if your graph approaches the same value at the ends, then we call that a horizontal asymptote. Y equals 1. Okay, now how do we find that horizontal asymptote? We'll talk about this more in detail when we kind of consolidate our learning, but you want to look at the degree of the numerator, which is x to the first, and the degree of the denominator, also x to the first. If these degrees are the same, we say that this function is even Stevens. The degree on top is the same as the degree on the bottom. Okay, and if the degree on top is the same as the bottom, you use the leading coefficients. So we have 1x minus 1. Oh, my dog is barking in the background, sorry. Hey, Remy, stop, I'm in the middle of a video. Okay, and so we have x minus 1 over x minus 2. And so we're going to do... Remy, down. She must see a coyote or something outside. All right, so we do lead coefficient divided by lead coefficient. So y equals 1 over 1. And so our horizontal asymptote is y equals 1. Okay, that takes a little practice. That's just kind of an intro to it, but we'll talk more about that when we summarize. Okay, the y-intercept, the x-intercept, this should be familiar, okay? So to find the y-intercept is where the graph crosses the y-axis. So we know the x value has to be 0, so we find f of 0. Okay, so we get, on the top we get -1, on the bottom we get -2. Okay, f of 0 equals 1/2. And so our y-intercept is 0, 1/2. Okay, x-intercept, same thing. We know that the x-intercept is when the function equals 0. So we're going to take x minus 1 over x minus 2. We're going to set the whole thing equal to 0. Now, a fraction only equals 0 when the numerator is equal to 0. So just take x minus 1, set that equal to 0, solve for x, and you get 1, 0. The function equals 0 when x is 1. All right, so the domain, what is x allowed to equal? X can be anything but 2 because that's where the denominator is 0. So in interval notation, we say the domain is -infinity to 2 or 2 to infinity. With parentheses, in inequality notation, we can just say x does not cannot equal 2. And then the range, notice that y never equals 1. So same thing, -infinity to 1 or 1 to infinity. If you're going to use inequalities, make sure you say y cannot equal 1 because we're referring to the y values there. Okay, so this is kind of a pretty basic rational function. We have one vertical, one horizontal asymptote, and then we have the intercepts. Okay, so in the next example, you'll notice that your graph, so let's go ahead and add the arrows at the ends of the graphs, and it looks like we have a line with a hole in it. Okay, so take a look at your function g of x minus 2 times x plus 1 over x minus 2. So x cannot equal 2 again, but notice this graph does not have a vertical asymptote. And the reason is that we have a factor of x minus 2 on the top and on the bottom. So we can simplify this function by crossing out the x minus 2's. So I can write this function as g of x equals x plus 1. If you have a value that causes the denominator to equal 0, but it can be removed, we call that a removable discontinuity, and that is represented by a hole. Discontinuity. Hopefully I spelled that right. A removable discontinuity, also known as a hole. So notice that the x value of the hole is 2. Okay, to find the y value of the hole, you're going to substitute 2 into the simplified form of the function. So we're going to find g of 2, and we get 3. And so your hole, or your removable discontinuity, is at 2, 3. So if we go back to number 1, we were not able to remove this x minus 2, so that's called an infinite discontinuity. We have a vertical asymptote. And the difference here is that we could remove the x minus 2's, and so that's a hole instead of an asymptote. Okay, now, because once we simplified, we don't have any other issues in the denominator, okay? A hole cannot also be a vertical asymptote, so this function has no vertical asymptotes. Okay, if we look at the graph, there's also no horizontal asymptotes. The function is not approaching the same value on the left side as it is on the right side, so we do not have a horizontal asymptote. Okay, now if we look at the degrees of the functions, of the numerator and denominator, the original function, before we simplified, the top has a degree of 2 and the bottom has a degree of 1. We call that top-heavy. Okay, if the degree on top is bigger than the degree on the bottom, then that is how we know there are no horizontal asymptotes. It's like the top crushes the bottom and there's nothing left. Okay, and the rules about horizontal asymptotes we'll have to practice throughout the first part of the unit. Okay, y-intercept, again, so with the y-intercept and the x-intercept, you just have to make sure that you use the simplified form of the equation in order to find these. Okay, so I'm looking at the simplified form of my function g after I crossed out my removable discontinuity. Okay, so the y-intercept is just going to be represented by g of 0, which is going to be 1. And then the x-intercept, if I set x plus 1 equal to 0, I get x equals -1. So that's how we get the x and the y-intercept. Okay, so we only have one single point here where there's an issue. It's the discontinuity happens at the point 2, 3 because of the hole. So our domain is going to include all numbers except for 2. Okay, so here's your interval notation and your inequality notation. And then the range is going to include all numbers except for 3. So we have our interval notation and our inequality notation. okay? All right, and in the last example, we're gonna look at one that has a hole and a vertical asymptote. Okay, so h of x, if we look at the function, we notice that, okay, let's put our arrows on first at the ends of our branches. Okay, so we have a hole at, it looks like 1, -2 is a hole, so it's discontinuous there. And then notice we also have a vertical asymptote here at x equals 2. And then we have a horizontal asymptote at y equals 0. I can tell that the graph is approaching 0 on the left and on the right. All right, so let's talk about how we know all of those by looking at the equation, okay? So if we look at h of x, we can simplify this. We can remove the x minus 1. So I'm going to write h of x equals 2 over x minus 2. Okay, so the removable discontinuity, the issue is x equals 1, so the hole happens when x is 1. And to find the y value of the hole, you're going to put 1 into the simplified form of your function. So we get 2 over 1 minus 2. And so that gives us, what did I do wrong there? Oh, I'm sorry, I put, oh yeah. So 2 over -1 is -2. So the hole is at 1 comma -2, okay? Now, even though I took out that hole, I still have an issue on the bottom. So the x minus 2 is still a problem. That is not a removable discontinuity. I can't get rid of it. So that is a vertical asymptote. So the vertical asymptote is found from the simplified form of the function. If you can't remove it, it's a vertical asymptote, okay? Horizontal asymptote is at y equals 0. So far we looked at a function where the top and bottom had the same degree, and then we had one where it was top heavy. And now look at this one. The degree on the bottom is bigger than the degree on the top. So we call this one bottom heavy. And if your function is bottom heavy, then the horizontal asymptote is automatically y equals 0. Okay, and again, these are rules that we'll talk more about, and I'll make sure we revisit them next week. All right, to find the x and y intercepts, make sure you use the simplified form of your function, which I have here. Okay, so h of 0 is going to be 2 over -2, so we get 0, -1. And notice, if I set this function 2 over x minus 2 equal to 0, a fraction only equals 0 when the numerator is 0. Well, the numerator does not have a variable. 2 is not equal to 0, so there is no x-intercept. And if you look at your graph, you can see that the graph is not going to touch the x-axis. All right, I have two domain restrictions. X cannot equal 1 and x cannot equal 2. 1 because there's a hole, and 2 because there's a vertical asymptote. And then the range, y cannot equal -2 because of the hole, and it does not ever equal 0 because of your horizontal asymptote. Okay? All right, so to summarize, what did we find? So rational equations can have what we call discontinuities. So non-removable discontinuities are your vertical asymptotes, which are invisible lines that the graph approaches but does not touch. And your removable discontinuities are called holes, okay? So this little table here kind of summarizes how you find the key features of a function. So if I give you a function f of x and I say it equals n of x over d of x, okay, here's some general rules. So the x-intercepts are the real zeros of the numerator. These occur when the numerator equals 0. The y-intercept is the point where the graph crosses the y-axis, and so you have to find the value of f of 0. Just a reminder to use the lowest terms form of your equation to find the x and y-intercepts. Okay, vertical asymptote, the real zeros of d of x when the function is written in lowest terms. So when you've taken out any common factors that represent holes. Okay, and then here is a summary of your rules for horizontal asymptotes. We're also going to talk about something called oblique or slant asymptotes, but we'll talk about that later in the unit. Okay, so we talked a little bit about these rules here, but if you need to revisit or study them, here's how we know the horizontal asymptote. So if the degree of the numerator is less than the degree of the denominator, then then your horizontal asymptote is y equals 0. Okay, so we kind of think of this as bottom heavy. There's something left on the bottom, y equals 0. If the degrees are the same, so you're even Stevens, you're going to use the leading coefficients to find the equation of the horizontal asymptote. And then if the degree on top is bigger than the degree on bottom, there's no horizontal asymptote. Okay, so we call that top heavy. Okay, and if the degree of the top is one more than the degree on the bottom, we have something called an oblique or a slant asymptote, and we'll have a whole lesson on that later in the unit. Okay, so I'm going to do 2 graphing problems with you, and then I'm going to have the sub turn the video off, and I'm going to have you do a couple check your understanding problems to practice on your own. Okay, so this first problem, the first thing that we're going to do is we're going to write the function in lowest terms. So in this case, I can factor a 2 out of the top, and I get x minus 3, and then I have an x plus 4 on the bottom. So it is indeed already in lowest terms. I can't cross out any common factors, so I'm just going to rewrite the function on the line. Okay, so there are no removable discontinuities, so I'm just going to write the word none. Okay, there is a vertical asymptote at x equals -4, because that's the value that will cause the denominator equal 0, and it's not removable. To find the horizontal asymptote, you're going to look at the degrees. The degree on top is the same as the degree on bottom. So your horizontal asymptote is going to be y equals, you're going to do leading coefficient over leading coefficient. So 2 over 1 is just y equals 2. To find your y-intercept, you're going to find f of 0, which is going to give you -6 over 4. And so your y-intercept is 0, -3/2. It's fine if you write -1.5. To find the x-intercept, I'm going to let my numerator, 2x minus 6, equals 0. And I'm going to solve for x, so x equals 3. So the function equals 0 when x is 3. Okay, domain. And now instead of intervals, we're just going to use inequality notation. So x cannot equal -4. And then for my range, we're going to have, look at the horizontal asymptote as y equals 2. So y cannot equal 2. All right, so to graph this, I'm going to go ahead and draw a vertical asymptote at x equals -4. I'm going to put a horizontal asymptote at y equals 2. I'm going to put my y-intercept at 0, -1.5. I'm going to put an x-intercept at 1, 2, 3, 0. And that's all we have. Okay, now you could use your graphing calculator to figure out where the branches go. Okay, but you're going to see that you can kind of use these asymptotes as a guide. I'm actually going to do the graph in a different color. So 0, -1.5, 1, 2, 3, 0. So your function is going to go through these 2 points, and it's going to approach but not touch your asymptotes. So I have one branch here, and then what we know from the previous examples is that the other branch is going to be in kind of this opposite quadrant. Okay, so this is a rough sketch, and that's good enough. Okay? All right, we're going to do one more together. Okay, so in this next one, I'm going to start by putting it in lowest terms. So this time I can factor my numerator into x minus 5 times x plus 2. And then I have an x minus 5 on the bottom. So my lowest terms of this function is going to be, I'm going to cross out my x minus 5s. And so I just get x plus 2. Okay, so I have a removable discontinuity when x is 5. To find the y value of my whole or removable discontinuity, I'm going to find h of 5 using my simplified lowest terms of the equation. So I just do 5 plus 2, and so the whole is at 5, 7. Okay, now I'm going to look at this form of my equation to answer the rest of the questions. Okay, I don't have anything left in the denominator, so there are no vertical asymptotes. Okay, we can think of it, if you want to look at the original, the degree on top is 2, the degree on bottom is 1, it's top heavy. So the top crushes the bottom, there are no horizontal asymptotes. The y-intercept, h of 0 equals 2, so my y-intercept is 0, 2. Okay, my x-intercept is when this function equals 0, so x equals -2. So -2, 0. And the only issue here I have is my whole at 5, 7. So I know that x cannot equal 5 and y cannot equal 7. Okay, so I'm going to go ahead and put a point at 0, 2. I'm going to put a point at -2, 0. And I'm going to put my whole at 5, 7. So 1, 2, 3, 4, 5, 6, 7. Okay, and what you'll notice is that, look at your lowest terms, h of x equals x plus 2. That's a line. So my function is just a line with a y-intercept at 2, a slope of 1. But because I had to cross out that removable discontinuity, this line has a hole in it. Okay, so my graph looks like this. Okay? All right, so I'm going to have the sub turn the video off there, and I want you to go ahead and try the remaining 2 examples, and then you can check your answers on Schoology. All right, thanks. I hope you guys have a good weekend.